Today we are exploring representation forcing for bottleneck-free unified multimodal models. A paper about teaching one model to understand images and generate them without depending on a separate image compressor.
What does unifying understanding and generation actually require from the model?
A unified multimodal model uses a shared transformer for both directions. It reads an image to answer questions, and it turns a text prompt into an image. But most so-called unified models still outsource image generation to a frozen variational autoencoder, or VAE.
Why is that frozen VAE a bottleneck, rather than just a useful tool?
The VAE latent space was trained separately for reconstruction. Its lossy compression limits the detail the unified model can recover, and the unified model cannot improve that frozen component through end-to-end training. Generating raw pixels removes that bottleneck, but it creates a harder learning problem. From one raw signal, the model must discover the scene layout and object identities while also rendering texture, edges, and color.
So pixel generation needs structural guidance, but using a separate VAE would bring the bottleneck back. Where does the paper get that guidance?
It reuses knowledge already learned inside the model. The understanding encoder produces features that capture objects, spatial layout, and scene composition. Representation forcing trains the decoder to predict a discrete version of those features before it generates pixels.
In the three architectures shown here, what changes in the representation forcing version?
The left design compresses images through a frozen VAE. The middle design removes the VAE, but sends text directly into pixel diffusion, so it lacks a structural scaffold. The right design inserts predicted representation tokens between text and pixels, entirely inside the shared transformer. The representation targets come from an exponential moving average copy of the joint image encoder. Online vector quantization maps each fetch feature to a discrete code, producing a spatial sequence that the decoder can predict one token at a time.
Why make the encoder features discrete instead of predicting the continuous feature vectors directly?
Discrete prediction turns each spatial position into a robust categorical choice. It also encourages the intermediate sequence to preserve high-level structure and discard fine detail, leaving pixel diffusion to handle the rendering. Later, the ablation shows this choice is essential. During training, the decoder receives one unified sequence text tokens, representation tokens, then pixel patches. Text and representation tokens use causal next-step-down prediction. Pixel patches can attend to one another and to all earlier text and representation tokens.
At generation time, there is no ground truth image for the encoder.
The decoder first predicts the complete representation sequence from the prompt. Those predicted tokens stay in context while iterative denasine turns Gaussian noise into the final pixels. No VIE and no external diffusion decoder are used at inference. Pixel generation uses flow matching. At time t, the noisy patch c sub t blends a clean image patch x with cosine noise epsilon. Small t means mostly noise, and large t means closer to the clean patch.
What is the model learning from that noisy patch?
It predicts the direction from noise toward the clean patch. The flow matching loss penalizes the square difference between the predicted direction and the target direction. Representation tokens matter because they tell this denasine process which high-level structure it should render. End-to-end training combines three jobs: predict the next text token, predict the next representation token, and generate pixels with flow matching. That shared objective is how perception features become native generation targets.
How do the experiments separate the effect of representation forcing from other design choices?
They train for controlled variance pixel plus RF, VAE, and VAE plus RF. The architecture, data, and optimization stay identical. Only the generation pathway and whether representation forcing is enabled are changed. The qualitative comparison makes the failure mode visible. Without representation forcing, direct pixel generation produces distorted object shapes and incoherent compositions. With representation forcing, the predicted high-level structure guides diffusion toward coherent layouts.
Does the quantitative result support that visible improvement?
Strongly. On the controlled gen-evil ablation, plain pixel space generation scores 0.5. Adding representation forcing raises it to 0.76, almost matching VAE plus RF at 0.77. The VAE pathway also improves, from 0.52 to 0.77.
Could simpler feature alignment provide the same guidance without predicting representation tokens?
Not nearly as well. Auxiliary alignment traces gen-evil from 0.25 to 0.43, while representation forcing reaches 0.76. Alignment shapes internal features during training, but RF puts predicted structure directly in the sequence that conditions pixels during inference. The discrete formulation is equally important. Continuous feature regression scores 0.26, essentially the same as having no guidance. Discrete representation tokens reach 0.76 because they avoid compounding vector errors and focus the intermediate stage on structure.
After those controlled ablations, how competitive is the full pixel space model against existing unified models?
Without a prompt rewriter, RF pixel scores 0.8 for Ungen Evil, above the BAGL baseline at 0.82 and equal to BLIP30. With the rewriter it reaches 0.88, matching the best reported unified models. On DPG bench it scores 80 for 0.15. These samples show the full model generating detailed images directly in pixel space at 1024 resolution. The key result is not merely visual quality. It reaches that quality without a separately pre-trained generative component.
The model also performs image understanding. Does adding generation weighting help or hurt that side?
Representation forcing improves pixel space understanding on 6 of 8 benchmarks. The largest gains include for 0.5 points on AI to D, for 0.3 on MMMU. Pixel plus or F also beats VAE plus or F on 6 of 8 benchmarks.
Were the understanding gains uniform across every kind of visual task?
No, the gains concentrate on object recognition, spatial comprehension, and scene-level perception, which fit the structural information carried by representation tokens. DuckFi QA drops by 2 points and chart QA drops by 0.4, suggesting precise text recognition and layout parsing receive less benefit. The encoder choice supports the same interpretation. DINOV3, whose self-supervised features preserve spatial structure, beats the language-aligned SIGL IP2 encoder on 4 of 5 understanding benchmarks. The representations are smatters because its structure becomes the generation scaffold.
What limitations keep this from being a fully native multimodal model already?
The model starts from a pre-trained large language model, rather than learning every modality from scratch, so fully joint pre-training remains untested. The work also covers still image generation only, not video or other temporal modalities.
What is the main lesson to carry forward from these results?
Representation forcing turns the model's own understanding features into predicted generation targets. That structural scaffold closes the pixel space quality gap, improves many understanding tests, and removes the need for a frozen generative latent space. That wraps up our explanation of representation forcing for bottleneck-free unified multimodal models.